Okay, so hope you have read the slides in this weekend. Okay, now it's done. Full screen. So if you have any questions, any doubt, let me know. So I'm trying to teach about with some pictorial way, okay, to understand about the origin of the primary kinetic isotope effect. So basically, if you replace hydrogen of a starting material with deuterium, the rate may be affected. If rate doesn't affect, then doesn't matter. This kinetic isotope effect will not be helpful to you to understand the mechanism. But if there is some effect, many cases it can affect, okay, especially the if CH or CD bond is being broken in the rate determining step, then definitely on replacing the hydrogen with deuterium, your rate constant will change and you will get a different value kh by kd rather than having one. Okay, it may be less than 1 or greater than 1, whatever I told in last two class. So I also told that in the primary kinetic isotope effect, especially if the CH or CD bond is being dissociated, homolytic cleavage dissociation of CH or CD bond, it is here in the rate determining step or in the final step, okay, then origin the kh by kd, the difference, the kh by kd will be more than 1.5. It depends on the what is the structure of the transition state, but those are the primary kinetic isotope effect. Value will be 1.5, kh by kd will be 1.5 to 6.8. Last time we also discussed that how we are getting the maximum value, theoretical value 6.8. This is based on these experiments as well as the calculations based on the RNS equations. That is basically the difference of the 0 point energy of CD and CH in the ground state. The ground state, okay, of the starting material. All right, so hope it is clear from now. Okay, we also told that, I think maybe this slide is the, okay, I forgot which slide is the last. So, but for most reactions, it is written in the top. I wrote it. In most reactions, bond is not completely cleaved, right? We will give many examples, but you know that in SN1 and SN2 reactions, when carbon bromine bond is being broken, this is being broken in the transition state, not completely cleaved. It doesn't matter it is SN1 or SN2 or any other kind of reactions. For most cases, the bond is not completely broken. It is right. It is undergoing cleavage. Okay, it is being broken in the rate determining step. So on those cases, so there will be a transition state and that will be a molecule also, right? So on that molecular transition state also have vibrational levels. It's not completely cleaved. So that transition state structure will be definitely, that will be different compared to the ground state structure of the substrate or starting material, right? It is here. So on those cases, if CH or CD, suppose here AH bond is being cleaved and BH bond is formed. This is the starting material left hand side, right hand side, this is the product. And in the transition state, suppose the hydrogen bond is being cleaved, it is being cleaved, dot dot dot, and pH bond is being formed, it's forming, it's not completely formed, but it's forming. So there is a kind of transition state whether the B will come close to each other and BH bond will form and AH bond will cleave. Suppose similar to like SN2 type of reactions. Suppose, okay. So on those cases, the transition state, it is involved like an A. It is the transition state will be kind of like A, H. Okay, we'll discuss more with examples. Okay, this is just like a rough A and B. This is will be the kind of transition state. Okay, right? So this is a molecule. So it will also have a vibrational levels in the transition state. So the kh by kd, it will all depends on, I think I told in the last class, right? that what is the difference between the 0-point energy of the ground state versus what is the difference between the CH and CD bond in the excited state or transition state. So which is faster, which barrier is lower for CH or CD? Someone also asked that which level is which. As I told, from the law, Hooke's law, or whatever the quantum mechanics law, that the vibrational frequency equations, it is inversely proportional to the square root of mu reduced mass. So since D has more mass than H, almost double, not almost double, it is double, almost double, then definitely always CD ground state energy level will be always lower than CH. So whose barrier is lower? Here CH barrier will be lower. Why? Because you can see in this picture the difference between the CH and CD in the transition state is lower compared to the ground state or starting material. Okay. So for getting clip of AH bond, the activation energy for CH bond, activation energy for CH bond cleavage will be, or AH bond, suppose it is the A, okay, C is equal to A, then cleavage of AH bond requires lesser energy compared to that of AD bond. Does it make sense? It is obvious. You can see the length or energy of the blue line versus the yellow line, right? Yellow is correspond to the barrier for CH or AH bond, and blue line, this is the blue line, right? So this is the barrier correspond to the AD bond. So blue is much larger than the yellow one. So KH by KD will be greater than 1. Okay, is it clear?
Yes, sir.
Yeah, this slide I also told last time. Again, I'm repeating. All right. So now next questions will that I told you a range. I'm talking about primary kinetic isotope effect, CH or CD or AH or AD bond is being broken. Here it can be AH or it can be AD bond. I'm talking about primary kinetic isotope effect. I'm not talking about secondary or inverse. Okay, let me finish primary first. Okay, so what is primary? AH or AD bond is being broken in the transition state. Okay. So now I told you the range of KH by KD is 1.5 to 6.8. Now the next questions will be that if it is 1.5, when it will be 1.5 or 2, or some cases why it is a range, for which cases it will be lower KH by KD, suppose 2, and what are the cases where you may see the higher KH by KD like 6 or more than 6 or 5. So the value of KH by KD in primary kinetic isotope effect will actually tell you about the nature of the structure of the transition state. Okay, about it will give some hint about the structure of the transition state. That is the second point I told you in the beginning. What kinetic isotope effect will tell you. It can also give a hint about the structure or geometry of the transition state. Okay, so let's see how geometry will affect the value of KH by KD in primary kinetic isotope effect. Okay. Okay. The first is, suppose the transition state is linear. See this equation. AH reacting with B, similar to like, suppose similar, okay, and it is forming A minus and BH. So AH bond is being cleaved and BH bond is being formed. So what will the transition state, as I drew in the last slide, that A dot 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 H and B. Okay, so this bond is cleaved and this bond is being formed, being is going on, right? And this is the transition state. Suppose this is a linear structure, obviously it may be linear or may be bent. Suppose it may also be something like this. A, H. Okay, wherever we are talking about H, it may be D also. Otherwise, you cannot get the isotope effect, right? It can be also bent. Okay, so this is a bent, right? And this is the linear. So look, just try to understand. Okay, I'm not giving any telling or discussing any equations, nothing. Just simplest pictorial explanation. This is a linear transition state, right? So in kinetic isotope effect, what you will do? You will replace H or D and find what is the difference between K. When H is there, that is KH. When D is there, KD. Okay, so if the linear transition state, we are talking about vibrations, right? All about the vibrations. So in vibration levels in CML 100 or maybe in high school, you know that the major contributions of the vibrations, even if you look at the IR spectroscopy, is the stretching frequency. You know that, right? Stretching, bending, right? So in the IR spectroscopy, in any molecules, okay? So major contributions or major energy is come or peaks, okay, and it is a higher in energy also. It is comes with the stretching. Now stretch can be symmetric stretching. It can be also asymmetric stretching. But for any kind of bond, symmetric stretching is the more prevalent because it will go just like you vibrate, right? Even if you put a spring, you will see the symmetric stretching, right? It will come upward or it will come downward, right? If you just expand a spring and then release it suddenly, it will vibrate, right? Then it will stop. So symmetric stretching is the most common type of mode of vibration. So what is symmetric stretching? It will stretch on the left hand side equally. Also on the right hand side, it will also stretch equally on the right hand side. So if you stretch, suppose this is the three molecules transition state A, H, B, A, H, and B. Now if you stretch, what will happen? A will move this side, B will move this side, and AH is the central atom. H will move or not? Suppose you have a spring, you have three balls. Okay, A is the left hand side ball, B is the right hand side ball. Okay, and C is the middle ball. Okay, so if you just hold the A and B balls and stretch outward, what will be the displacement of the middle atom or middle ball? Will it displace or it will move in case of symmetric stretching? Yes or no?
No, no.
No, this is the middle and you are giving equal force on left hand side, on right hand side, right? It is not in the bending mode also. Okay, the symmetric, you are pulling A and B outward and with equal force. So the movement of H will be remain same. Am I correct? So you can see here, I wrote it here in the symmetric stretching, if the transition state is linear, central atom is fixed. It will not move. Am I correct? Yes or no?
Yes, sir.
Now the problem is not problem. Okay, this is good. If it is H or D or T, doesn't matter what you are giving. Will it affect the vibrations of H or central atom? No. If it is H, if it is D, it is not vibrating. Central atom is not vibrating for this case. Symmetric stretching of the linear transition state. So it doesn't matter what is the mass of the central atom. If it is H, if it is D, if it is T, or maybe some other atoms, it doesn't matter. The vibration level will not change by replacing the central atom. Am I correct? The central atom is not moving. Even if it is moving a little bit. So the vibrational levels or vibrations will not be affected of the central atom if you replace the central atom with other isotopes. So you can see here on those cases, the CH or CD bond ground state will be almost equal. Does it make sense? Because transition state, it cannot recognize it is the H or D in the middle, right? Because it is not vibrating for in this special case. So the vibration level gap, there will be a gap, definitely there will be a gap, obviously. Because zero ground state energy in the reduced mass, okay, there will be little vibrations always, okay, but the gap will be minimal. You can see here, okay, they almost submerged. In those cases, this is this. On those cases, this is the reaction energy profile diagram, reaction coefficient versus potential energy. You can see on those cases, Kh by Kd will be mainly dependent on the difference of 0 point energy in between Ch and Cd in the ground state. Okay. All right. And what is the value of this? What is the value? How much Kh by Kd you can get? It is here 6.8. It is similar case like this. Okay, it is CH or CD bond are almost same, right? So whatever the energy differences of the Kh by Kd, this will be difference between the ground state of CH or CD. And what is the maximum value? 6.8. So if the transition state is linear, perfectly linear, then your Kh by Kd will be close to 6.8. Okay, or if it is almost linear, definitely it will be less than 6.8. If it is little bit of, it is almost linear or little bit of bend, then what will happen? You will see similar kind of situations. CH and CD bond will not be same level, but there will be a small difference, right, in the excited state. On those cases, Kh by Kd will be less than 6.8, right? But all depends on what is the gap of Ch by Cd 0 point energy in the transition state. So if it is perfectly linear, you will get high value of Kh by Kd, maybe 4, 5, 6, right? If it is perfectly linear, you will get close to 6.8, above 6, if it is perfectly linear. If it is little bit of bend or depends, okay, how much vibrations of H is there, it will be the Kh by Kd value will be lesser than 6.8, but still it will be very high, like 4, 5, 6, like this. Okay, is it clear?
For excuse me, sir.
Hello,
Sir, for symmetric stretching, do A and B have to be the same atom?
same atom means
Like
A and B.
yes.
That's what I'm telling. If it is the same atom, okay, A and B, you are correct. As long as in the symmetric stretching on the left hand force and right hand force is equal, okay, right, then H will be fixed, but A and B may be different atom, right? So in symmetric stretching, A and H vibrations and B and H vibrations may not be same. So on those cases, H might be little bit of vibrations, little bit, right? It may possible. On those cases, definitely Kh by Kd will be also high, but you may see Ch by Cd some differences there. Do you understand?
Okay.
So CH Cd bond will level equally like this if A and B are suppose same atom, same identical symmetric vibrations. Okay, but if it is little bit of fluctuations, like A and B are the different atoms, or H has some kind of vibrations little bit, okay, then definitely this will not be in the same level. It will be in a different level, but the gap will be very small. Okay, so in the transition state, if gap is getting larger, then your Kh by Kd will decrease. Am I correct?
Yes, sir.
Yeah, I will discuss more. Let's discuss next slide, because this is the just like a complementary. So as I told, if it is the perfectly linear, and yeah, I didn't see your name. So whoever asking, suppose it is perfectly symmetric stretch, left and right hand side. If A or B are same, then center atom will be fixed. if central atom, some reasons, if it is a little bit of move or more movement, then the energy difference between this, there will be an energy difference of the CH and CD in the 0-point energy in the transition state. On those cases, KH by KD will be more and more lower compared to 6.8 value. 6.8 value is the highest. Okay, when central atom is the fixed. I'm telling you, right? So if the transition state is bent, transition state is bent. I told it in last time, last slide. If it's bent, then what will happen? You can see now, if it is H or D, it will also have the vibration, isn't it? It will vibrate this way. Okay, so as long as whenever you will see that there is a H and D is vibrating, definitely in the transition state, like here is a bent transition state, there will be a gap between CH and CD in the transition state. If it is perfectly linear, CH and CD is almost in the same level. On those cases, KH by KD will be greater than 6. Okay, highest value will be 6.8. Okay, but it depends on the nature of the, as I told, that the value can tell you, give you some idea about the geometry of the transition state. So if it is the bent transition state or bent transition state of the rate determining step, then value will be lower than 6. So how much bent? It all depends on what is the value. If it is 2, means it might be this angle will be 90 degree. Okay. If it is almost 180, then you may get 5 or 6 or above 6. Okay. Why? Because in bend there will be vibrations of H. So if you replace with H with D, then definitely D will be affected. The mass will also affect the vibrations a lot. So there will be a difference of the 0-point energy in the excited state. So definitely, obviously, the gap will be less because there is already a gap in the excited state. On those cases, KH by KD will be less than 6.8. So what will be the KH by KD value? All depends on what is the angle between A, H and B. Okay. You take 1 minute or 2 minutes. Just try to grasp what I told you. If it's not, I will repeat again. Okay, I'm not discussing any equations. Just you need no need to remember anything. Okay, only you can understand what is the origin of the primary kinetic isotope effect. What will be the value based on the purely understanding. Okay, so take a 2 minutes break. Think about that, and then you tell me if you have any questions. Whatever the questions you have. Okay. If you have any questions, you can tell me. Questions? No questions? Is it clear? Then I will go
Yes,
next.
sir.
Okay. Okay, so now let's go. So now I'm now going to tell you about the examples. So the first example. This is a kind of elimination reactions. Okay. So suppose this is the case 1. The red color. Okay, the orange color. This is the propyl bromide. The treatment with sodium ethoxide in ethanol gives propene. Okay, this gives a propene. So what is the mechanism? You can see this is the same thing. You are replacing the CH2 of the middle carbon atom with CD2. This CH2 you are replacing with CD2. Okay, same reaction. So what will be the product? It will be the also the propene, but middle carbon will have CD bond. So kH by Kd, you can see the energy kH by Kd, the value is almost close to 6.8. Okay. So first thing, what does the kH by Kd means? Can you hear me? Yes.
Yes, sir.
Primary
Okay.
kinetic isotopic effect.
So first thing is the first thing. Okay. Same. Okay. If I ask you quiz, so what can you interpret? First thing will be it is a I am actually I don't know why this can like happen like this. First thing is the 1 degree. 1 degree means primary. You know that, right? 2 degree means secondary. Primary kinetic isotope effect. First thing, you will close your eyes, you will tell it is more than 1.5 means it is kinetic. Primary kinetic isotope effect means what means CH or CD bond is being broken or broken. It doesn't matter. CH or CD is broken in the rate determining step. First conclusion from this value, right? Okay, now you can draw a possible mechanism or what is going on in the transition state. Okay, first of all. So this is an example of there are two kinds of transition state is possible. Two kind. Okay. So similar to like SN1 and SN2. One might be E2. E2 means two molecule bimolecular. You can see the ethoxy is attacking on the CH. Okay. And then CC bond is forming and CBr bond is leaving. Okay, makes sense. So this is a concerted process. Another kind of mechanism is possible, similar to like SN1. The first carbon bromine bond will break. Okay, to form a carbocation. Then next step, what will happen next step? The CH bond will be broken, right? So minus H plus and then alkene will form. Does it make sense? So there are two kind of rate determining step is possible. The first one is still E2 reaction similar to SN2. Okay, these elimination reactions. Okay, so it's concerted process. Second one is the second one. So what will be the red law? So first you need to determine the red law. So what can you expect? So you don't know which is correct. So first you need to do the red law. Red law you may see that this is the first order with respect to methoxy. First order with respect to this starting material both. One first order of this. Okay, you may see. So if it is the bimolecular reactions first order on both, then the E2 is correct. If you see that this is only first order but zero order with respect to methoxy, then E1 is correct. Am I fine? Just try to follow what I am telling. Okay. So now let's see, but one is not enough. what might be of how kinetic isotope effect is telling? So kinetic isotope effect is telling that CH or CD bond is being broken in the transition state or a deriving step. So which is correct, E2 or E1? You tell me.
Say 2.
E2, because you can see here CH bond is being broken, right? In the rate determining step. In E1, this bond is not being broken. It will be broken in the next step. Okay, so this cannot be rate determining step if it is KH by KD is 6.7. Problem solved, right? All right. You can see here the case 2. This is a kind of T-butyl bromide in water, not T-butyl bromide. This is the ethyl dimethyl methyl bromide. Okay, you will tell. Okay, what is the nomenclature? 1 2 so 1 2 so 2 dimethyl propyl bromide. This one. Okay, in water it gives isoprene. If you replace the CH2, this H2 with D2, now KH by KD is telling the value is 1.4. So what does it mean? You can see there is a marked contrast. This for case 1 and case 2, you can see KH by KD is 6.8, but this case is 1.4. So 1.4 means this is a secondary kinetic isotope effect. Okay, so it is here most likely KH or KD bond is not being broken in the rate determining step. First conclusion, right? So what might be the possible transition state? It might be the possible transition state of E1 case. This is an example of E1 case. Yeah. And why this is the difference? Because this is the whatever the carbocation will generate, this carbocation will be a tertiary carbocation. It will be more stabilized, right? You know that from your high school, right? Plus R effect, inductive effect, the tertiary carbocation will be more stable than secondary. So here you will get, if it is carbocation, you will get the secondary. This is not stable much. But if it is T-butyl like SN1 type of reactions, it will be more stable. Okay, so carbocation, the first step is rate determining step carbocation, but on that case CH or CD bond is not being broken. That makes sense. You see how powerful is this KH by KD value it can indicate. In the first case, not only for that, very high value 6.8 also will tell what will be the geometry of the transition state. It tells that it is close to the linear transition state. So whatever the bond angle here, this bond angle will be close to 180. Even though it is not drawn 180, okay, but it will be a close to 180. So this value can tell what will be the probable geometry of the transition state. Not only for that, it will also tell, that is the more important than transition state geometry. That is the who on the rate determining step whether CH or CD bond is broken or not. So based on the value, you can deduce the possible rate determining step of a reaction. Is it interesting? Hello?
Yes, sir.
Yeah, not only for that, if I tell you this is the mechanism, you can predict. Suppose in a quiz I am giving you these examples C1 and this case 1 and case 2. I may ask you, simplest question I told you, right? I may ask you, you tell me at least 3 experiment or maybe 2 experiment, okay? Because I have not discussed all the experiment yet. Suppose I can tell you, yeah, deduce 3 experiment. What type of 3 experiment you will do to differentiate these 2 pathway? Okay, I may also tell you the transition state E1 and E2 transition state. How can you distinguish? So first one will be the rate law. So you need to write that for if the transition state is E2, then Red law will be the first order with respect to both starting material, right? Sodium ethoxide and this propyl bromide, right? So it will be a second order kinetics. But if we discuss the E1, then it will be a total first order kinetics. Not only for that, you may also need to tell the activation parameters. The second thing, what will be the activation parameters? What about the changes of del S of activation for E2 case? It will be positive or negative?
Positive. Oh, sorry. For E2, it's negative.
It will be negative because two molecules are coming close to each other in the transition state or determining step, right? Yeah, and here CBr bond is being broken. Finally, you are getting two molecules or two ion, so it has more more disorder. Okay, so entropy of activation will be positive. I told you, right? Next is the isotope effect. So we need to tell them that if you replace, you need to tell them, not them, you need to tell me in the writing, in the question answer, your answer sheet, right? That if you replace CH by CD, then you may find that KH by KD will be greater than 1.5. So I have taught you 3 experiments so far how to deduce a mechanism. And what is the mechanism? What is the mechanism? So you have two cases. You may have E1 or E2. So these 3 experiments will disprove another one pathway. So mechanism is that pathway that disproves all other pathway. Okay. So if from this red law for case 1, you have 3 experiments. From the 3 experiments, you can disprove that E1 is incorrect. So probably E2 is correct. Probably proposed mechanism. E2 might be the proposed transition state in the red determining step, not E1, because based on the 3 experiments, you disproves E1 pathway for case 1. Case 2 is just opposite. Am I correct? Is it clear? Oh my God, it's only 3 minutes left. We have a lot of mechanism. Okay, you should study. Okay, slides are already shared. Okay, so please study. Okay, so this is my, okay, I'll stop with more examples then. Okay, and then next class I will discuss about the origin of the secondary kinetic isotope effect, inverse, and then I will finish. Okay, so more examples. You can see here, these are radical mechanisms. Okay, the toluene CH3, if you have some suppose NBS or okay, that is a bromine radical in light, then it can generate a radical. So if you replace H with D, you may see KH by KD is 4.6. So what does it mean? What will be the possible transition state in the red determining step? It looks like this kind of transition state, H and Br, right? And you can see it is close to 5. So it is almost very close to a linear transition state. Okay. Not only for that, it is telling in the red determining step, CH or CD bond is broken in the red determining step because it has 4.6. All right. Okay. You can see this is all the examples of primary kinetic isotope effect. You have OH minus for the second case. It is attacking here. This is the examples of E2 elimination. So here you can also tell what is the transition state. Next steps. Here CH or CD bond is being broken. You can see KH by KD value is 4. All right. Same thing here. You can see KH by KG, KD for third case is 6.1, very high. That means that CH or CD bond is being broken in the red determining step. All right. Okay. Anything else? So here is more example. Here is more example. There is one of the example I will discuss next time. Okay, that you can see this is the nitration. You know from your high school that for nitration of benzene to nitrobenzene, okay, is the industrial reactions, that how the nitrobenzene is produced by the nitration of benzene. But in those cases, you can see here CH bond is converting into CNO2 bond. But you may think that CH or CD bond may be broken in the rate determining step, but it is not. KH by KD is coming close to 1. So you can see the isotopy effect is telling what about the mechanism or pathway or rate determining step of this important reaction that you know from your high school is the nitration of benzene. It is produced in ton scale in industry. Here CH or CD bond is not being broken in the rate determining step. Okay, maybe in the slide we have already, in the next slide we will discuss next, but you think or maybe you practice. So what might be the possible mechanism? Whatever you may thought before, that for in these cases it might be probably like the CH, because it is CH is converting to CNO2. So it is a high chances of CH or CD bond is being broken in the rate determining step. But your experimental value is telling no, we are wrong. So that indicates that there will be one step where benzene CH or CD bond or CH bond is broken, but that is actually not the rate determining step. That is not, unlike here. Okay, here also CH is converted to CBr bond, but here CH or CH bond is broken in the rate determining step, but not in case of benzene. Okay, how do you know? The value of KH by KD. So interesting, so important experiment, so important. Okay, I may ask you the questions of the same example, maybe 5 marks questions. So you tell what is the difference of this mechanism based on this KH by KD value difference.
So when it's 1.5, it's primary or secondary?
Which one?
Second example, when it's 1.5.
1.5. So you tell what is telling. So it will be the primary.
Primarily, right? Yes. Sir.
It is the primary.
Yeah, but can we see that every time? Because here it's easy to tell, like because we can.
Okay, look. If it is normally okay, it is not like an hard and fast rule. Okay, that 1.5. But secondary kinetic isotopic normally values come like 1.3, 1.4, maybe less than 1.2 also.
Okay, sir.
Okay. So if it is close to 1.5, you may tell it is a primary kinetic isotopic effect. The secondary, I will discuss later. So values come now normally like 1.3, 1.2, 1.25, 1.11. Okay, something like this. Okay.
Yes.
Anything else? Anything else? No? Okay. So slides are already been given. You please read. And Saturday will be the quiz at 6 o'clock, 6 to 7, 10 together. And yeah, and I will see you on day after tomorrow.
Syllabus will be till taught, sir.
Huh?
Syllabus will be till Wednesday, right? For quiz.
Tell me again.
Syllabus for quiz.
Syllabus will be quiz for me until Wednesday. I will finish the isotope effect on Wednesday. Okay, until isotope effect. If I teach even very slowly and it can go on Thursday, that's okay. But I think I need one more class, okay, to finish the. So primary is done. Okay, primary is done. So next I will talk about the secondary. So that we will finish on next class. Yeah. Okay.
So will the portion taught before minors also asked in Shashankdeep sir's part?
Okay, I will tell you tomorrow. Let me ask him today.
Okay, thank you, sir.
Yeah. Or maybe today, even today night, I will email you. Okay, so what will be the syllabus for his case? Okay, yeah. And my case's syllabus is just very short, so you should not be worried. All right, and see you on day after tomorrow, Wednesday. Bye bye.
Thank you, sir. Thank you, sir.